Hello, this is Math 2115, alternate delivery for 24th March 2020. I'm going to start with a little bit of a paradigm shift. In the same way that we have talked about trees being flexible, and that's a good thing to do, as I was working through some very complicated inequalities last night for today's presentation, I realized that these would be much better done in class in a live setting. And then I said, why not? We may return to class. I have contingencies if not, but we may. And so I decided to change gears a little bit and talk about something that is maybe more readily completed in a YouTube kind of format, and that will be the topic of graph theory and trees. So we're sticking a pin in the discussion of analysis of algorithms and the associated inequalities, and we'll return to that later for sure, but not today. So today's topic is theory of graphs and trees. And there's many applications of this. We've seen one already when we talked about relations. In chapter 3, we could describe a relationship in terms of digraphs. There are other applications which include using graphs and trees in the study of decision problems, chemistry, data storage, computer language syntax, and even transportation networks. The subject of graph theory began in the year 1736 when the great mathematician Euler published a paper giving the solution of the following puzzle. The town of Königsberg in Prussia, now Kaliningrad in Russia, was built at a point where two branches of the Pregel River came together. It consisted of an island and some land along the banks. These were interconnected by 7 bridges, and I'll show you a picture of that in a moment. But the question was this: is it possible for a person to take a walk around town, starting and ending in the same location, and crossing each of the 7 bridges exactly once? That means once and only once. So let's see about the picture. So here's the picture. On the left-hand panel, you see kind of a aerial graphic rendering of what happened, and the bridges are shown in blue. You see on the left panel a more stylistic drawing of what was going on. And Euler, in his analysis, realized that it really didn't matter the shape of B, the shape of C, or the shape of D. We could collapse those to the point that really only thing that mattered was how were they interconnected. And so he did this. Euler not only started the study of graph theory with this, but also by shrinking these, he really was giving a nod to a mathematical field of study called topology, where you deform shapes into things that are considered topologically equivalent for the considerations of the problem. So right now we're going to look at the graph version of this map and consider that. So, in terms of this graph, the question becomes the following. Is it possible to find a route through the graph that starts and ends at the same vertex, one of A, B, C, or D, and traverses each edge exactly once? Equivalently, it could be stated, is it possible to trace this entire graph, starting and ending at the same point, without ever lifting your pencil from the paper or crossing an edge more than once? Now I want you to pause the video, take a few minutes to think about this. Can you find a route that meets the requirements? Please try it. Pause now. Okay, I'm back. Let's press play and see how you did. Now, you probably were frustrated because you continually found yourself at a vertex that does not have an unused edge on which to leave, while elsewhere there are unused edges that still must be traversed. If you start at A, for example, each time you pass through B, C, or D, you end up using 2 edges because you have to start it and come in one way and out the other. So if it is possible to find a route that uses all the edges of the graph and starts and ends at A, then the total number of arrivals and departures from each of Vertex B, C, and D must be a multiple of 2, or in other words, what we will call the degrees of the vertices B, C, and D must be even. But they are not. The degree of B is 5, and the degree of C is 3, and the degree of D is 3. Hence, there is no route that solves the puzzle by starting and ending at A. Similar reasoning can be used to show that there are no routes that solve the puzzle by starting and ending at B, C, or D either. Therefore, it is impossible to travel all around the city, crossing each bridge exactly once. Travel in graphs is accomplished by moving from one vertex to another along a sequence of edges, and in the graph below you can go from U1 to U4, taking F1 to U2 and then F7 to U4, and this can be compactly represented by this following string. Or you could take a more roundabout route that's shown with this more involved string. Certain types of sequences of adjacent vertices and edges are of special importance in graph theory. Those that do not have a repeated edge, those that do not have a repeated vertex, and those that start and end at the same vertex are of special importance. Let's look at the definition, or in fact a bunch of definitions. Let G be a graph and let V and W be vertices in G. A walk from V to W is a finite alternating sequence of adjacent vertices and edges of G. Thus a walk has the form of vertices and edges layered together, where the V's represent vertices, the E's are edges, and each of the vertices are endpoints of edge. The trivial walk from V to V is a single vertex. A trail is a walk from V to W that does not contain a repeated edge. You might pass the same landmark twice, but through different paths. A path from V to W is a trail that does not contain a repeated vertex. And so, again, a lot of definition. A closed walk is a walk that starts and ends at the same vertex. A circuit is a closed walk that contains at least one edge and does not contain a repeated edge. It's a closed walk, so it starts and ends at the same vertex, but that's a circuit. A simple circuit is a circuit that does not have any other repeated vertex except the first and the last. You don't go by any landmark twice. Now, I'm going to suggest that on the next slide, you pause, because what you want to do is there's going to be an exercise, and I want you to understand the definitions before I ask you to do the exercise. So on the next slide, pause and make sure you capture these ideas. So pause here. For ease of reference, these definitions are summarized below here, and this allows you to determine what is a walk, a trail, a path, a closed walk, a circuit, and a simple circuit. You can see that there are differences among them. Often a walk will be specified unambiguously by giving either a sequence of edges or vertices, and that can be done. But make sure that you save this in your notes before you go on, because I will be asking you to use this in a later example. So for example, in this graph below, E1, E2, E4, E3 refers unambiguously to the walk that goes from those, because that's the only way you can get from those vertices are through those edges. On the other hand, E1 is ambiguous if used by itself to refer to a walk, because that could either start at V1 or start at V2 and go the other place. So you want to make sure that when you're specifying these, there is no ambiguity. Similarly, if I just refer to the vertices, that refers to the walk that we have here. V1, E1, V2, E2, V2, we did the loop, and then it is E3, V3. Note that if a graph does not have any parallel edges, then any walk is uniquely determined by its vertices. There's not two ways to get from one place to the other. Okay, now this is the problem I was referring to where you'll have to do that. So what I'm asking you is in the graph below that you can see there, determine which of the following walks are trails, paths, circuits, or simple circuits. And you can see A through F, and so please pause, do this work, come back, and we will see how you did. Let's see how you did. A is a trail but not a path. B is not a trail because it has a repeated edge. C is a circuit, but it's not a simple circuit. D is a simple circuit. E is a closed walk, but it's not a circuit because the edge E1 is repeated. And finally, F is not a circuit, it is a closed walk, and it's also a trail. A graph H is said to be a subgraph of a bigger graph G if and only if every vertex in H is also a vertex in G, every edge in H is also an edge in G, and every edge in H has the same endpoints as it does in G. Okay, so if we have a graph that has a vertex v1, v2 set, and an edge set that is e1, e2, e3, where the endpoints of e1 are v1 and v2, the endpoints of v2 are v1 and v2, and e3 is a loop around v1, you want to list all the subgraphs. First step is drawing the graph itself, and then you'll draw the subgraph. So please pause, do the problem, and come back, and we'll check your work. Pause now. Let's see how you did. Okay, so your picture should look like this from a connectivity standpoint, and there are 11 subgraphs. And you can think about them, grouping them systematically according to those that do not have any edges, those that have one edge, and those that have two edges, and those that have three edges. Here they are. Many of these examples are illustrations of the kinds of problems I may someday ask you to do on some kind of an assessment. Now, we go into another concept now. This is the concept of connectedness. And it's easy to understand the concept of connectedness on an intuitive level. And roughly speaking, a graph is connected if it's possible to travel from any vertex to any other vertex along a sequence of adjacent edges of the graph. But realize that an edge has vertices on each end. The formal definition of connectedness is stated in terms of walks, and I will go over this with you. And we also even have a formal definition. So if G is a graph, two vertices V and W of G are connected if and only if there is a walk from V to W. The graph G is connected if and only if, given any two vertices V and W, there is a walk from V to W. Symbolically, G is connected if and only if for every vertices V and W in G, there exists a walk from V to W. And if you take the negation of this, you will see that a graph is not connected if and only if there exist two vertices that are not connected by any walk. Okay, so which of these graphs are connected? Please pause, do the work, and then we will return and see how you did. Pause now. Let's see how you did. Clearly, A is connected and B is not. C is not connected, but to understand why C is connected, recall that in a drawing of a graph, two edges may cross at a point that is not a vertex. It's not really a junction, it's not an official edge. So the graph in C actually can be redrawn as shown here, and there are three distinct subgraphs of this. three distinct connected subgraphs. I guess I should say it that way. Now here are some useful facts, and these could be theorems. Someday these actually could be an exercise, so you might want to think about how would you go about proving them. If G is a graph, and if G is connected, then any two distinct vertices can be joined by a path. If vertices V and W are part of a circuit in G, and one edge is removed from the circuit, you can still find a trail from V to W in G. If G is connected and G contains a circuit, then an edge of the circuit can be removed without disconnecting G. More definitions, but now we're talking about connected components of a graph. So a graph H is a connected component of a graph G if and only if it is a subgraph of G, it is itself connected, and no connected subgraph of G has H as a subgraph and contains vertices or edges that are not in H. So what this kind of can be distilled into is that any graph is a union, with quotes, air quotes around it, of its connected subcomponents. Okay, so here we have a problem for you to explore. So what we want to do is find all connected components of the following graph. Now that whole thing is the graph G. So what you're going to do is pause, work the problem, see how you did, and then we'll hit play and return. Well, there are three connected subcomponents, H1, H2, and H3. The first line is the one we call H1, and H1 is the graph that we see on the far left. The next line is the one in the middle, and the third connected component is the subgraph that we see on the far right. Now we're going almost all the way back to the beginning of the lecture, because now we're going to generalize what Euler did. So let G be a graph. An Euler circuit for G is a circuit that contains every vertex and every edge of G. Every vertex and every edge, and it's a circuit. That is, an Euler circuit for G is a sequence of adjacent vertices and edges in G that has at least one edge, starts and ends at the same vertex, and uses every vertex at least once, and uses every edge of G exactly once. That's called an Euler circuit. This is a key theorem, and this is the one that we sort of informally discussed before. But if a graph has an Euler circuit, then every vertex of the graph has positive even degree. Let's look at the proof. Suppose that G is a graph that has an Euler circuit. We must show that any vertex of G is of even degree. So let V be any particular but arbitrarily chosen vertex of G. Since the Euler circuit contains every edge of G, it contains all edges incident on V. Now imagine taking a journey that begins in the middle of one of those edges adjacent to the start of the Euler circuit and continues around the Euler circuit to the end in the middle of the starting edge. And we're looking at the figure that is down there to talk about starting in the middle. There is such a starting edge because the Euler circuit has at least one edge. Each time V is entered by traveling along one edge, it immediately exited by traveling along another edge, since the journey ends in the middle of an edge. Because the Euler circuit uses every edge of G exactly once, every edge incident on V is traversed exactly once in this process. Hence, the edges incident on V occur in entry-exit pairs, and consequently, the degree of V must be a positive multiple of 2. But that means that V has a positive even degree, as was to be shown. So that's the end of a much more formal proof. Now recall that the contrapositive, this goes all the way back to the chapter on logic, that the contrapositive of a statement is logically equivalent to the statement. And the contrapositive of the theorem that we just talked about says, if some vertex of a graph has an odd degree, that means it's not even, then the graph does not have an Euler circuit. This is a useful contrapositive, as contrapositives often are. So here is a problem. I want you to tell me why the graph below does not have an Euler circuit. In fact, more generally, I could have said, here is a graph. Does it have an Euler circuit or not? If it does have an Euler circuit, tell me what it is. If it does not, explain why it does not. Pause now, find an answer, and we'll return and see how you did. Pause now. Okay, the solution is not too bad. What we do is we realize that vertices V1 and V3, I'm looking for V3, yeah, both have odd degree 3, and that is odd. Hence, the graph does not have an Euler circuit. Now, we could consider the converse of that. If every vertex has even degree, then does the graph have an Euler circuit? Is that true? And you might think about that, but the answer is no. There's a graph G such that every vertex has even degree, but G does not have an Euler circuit. In fact, there are many such graphs, and the graph below is one of them. Now, you might notice that that graph is not connected. So it turns out, although the strict converse is false, if we modify it to talk about what happens if you have positive even degree and the graph is connected, then we can prove that the graph has an Euler circuit. The proof of this fact is constructive. It contains an algorithm to find an Euler circuit for any connected graph in which the vertex has an even degree, and is an important theorem that we're going to be proving next time. But now, more than ever, time is precious. Each day must count. Do the math. It will make you strong.